This is my talk. It's about deep learning for QSAR, a mysterious four-letter abbreviation. So I'll just start off by talking about me, very selfish, whatever. Oh, this has gone out the wrong way, is it? Yeah, damn it. This has gone the wrong way. So yeah, my name is Rich. I'm a third-year PhD student studying chemistry at Cambridge University. Pictures. Has anyone been to Cambridge before? Yeah, loads of people. So yeah, if you haven't, come and visit us. We've got beautiful chapels. We've got lovely bridges built by genius mathematicians, apparently. Fantastic colleges. This is St. Catherine's, which is actually the best college. Yeah, just so happens to be mine. And absolutely beautiful chemistry departments, really the jewel of the city. So in this chemistry department, this is my group. My PI is Dr. Andreas Bender. This is his face. We always have to put the face in. We've got 20 PhD students, 5 postdocs, and work on cheminformatics and bioinformatics problems. So this is basically chemistry and biology in a computer. We've got all of these different topics. If you're interested, come and talk to me, or even send an email to my supervisor. Here's some pictures. And yeah, we collaborate widely with industry and academia, and we're growing quickly, so definitely come and talk to us. So why am I here at PyData? Well, I learned to program only 3 years ago, so that's basically at the start of my PhD, and I use 3 languages: JavaScript, R, and Python. Yeah, and I love Python. It's definitely the best. So my talk, deep learning for QSAR. I was toying with putting 2 words in here. I thought it might engage lots of people's interests, but do I even want lots of people's interests? I'm not sure. So yeah, that's deep learning. It's really just unreasonably good. I could just leave it like that, but it's good for image recognition, speech recognition, natural language processing, and many more things. It's really cool. So many good applications. Everyone's got their favorite. Mine is this automatic captioning thing. So what it does is it takes a little, takes an image, and not only can it recognize people in the image or objects, it can actually tell you what is in the object, in the image, as just a normal English sentence. It's incredible. And not only that, you can just ask what was that word? What made you think that? And it'll tell you that. So really, if you can do something as complex as that, I thought, man, I'm gonna use these. I'm gonna use these for my work. This will help. So yeah, it was all aboard the deep learning hype train for me. So now, QSAR. This is probably. I'm not sure if you've read the information or not. Lots of people might leave after they hear what this is. They thought it was some sort of spaceship. So this is quantitative structure-activity relationship, and this is sort of I don't know, a summary of what it means. The basic assumption is that all molecule-based I can't read. Yeah, you can tell I'm a programmer. The basic assumption for all molecule-based hypotheses is that similar molecules have similar activities. So that's quantitative structure-activity relationship. Thanks, Wikipedia. So what does the Q mean? Quantitative. It's a regression. What's structure? It's one of these. Seeing some people, yeah, chemistry is not always that popular, but this is fairly tame, so bear with me. This is caffeine, if anyone didn't notice. It's what I've got here. Lovely. So if you haven't seen any of these before, these are atoms, the sort of nodes in this graph, and bonds are the edges. And we, obviously, being chemists, we need to be silly and leave out all the carbons. That's just what that means. So A is for activity. And it's a very broad term. We use it everywhere in cheminformatics, bioinformatics. It could mean anything, really. It's just very, very unhelpful. It could be a protein affinity, protein inhibition or activation, cell toxicity, phenotypic responses, even physical properties, although sometimes we'd say QSPR rather than QSAR. So A tends to be biological. We're going to be looking at protein affinities in this little talk. So this is sort of like an idea of what we're trying to model. Fortunately, we're not going to be doing lots and lots of physics. But you see, this is basically caffeine coming, floating, and just sticking into the A2A adenosine receptor. That's basically how you stay awake. And people say don't do live demos, but I just. So how do you measure these? You use one of these, and you have to do these sorts of plots here. You change the concentration and measure the activity. It's very laborious, which is why you use one of those research students. So finally, R is for relationship, and it's just basically talking about mapping. You map molecules to a number, and hopefully also include a Y. We love random forests, and feature importances is always the Y. So there's quite a lot to compete against. So what is it good for? Absolutely nothing? Probably not. The basic idea is drugs. For Big Pharma, just needs every help it can get because testing drugs is very, very expensive. And it would be good to virtually screen out compounds that are unlikely to be good drugs rather than spending all the money testing them. It would also be good to know how any drugs that already exist actually work. That's what we call the mode of action. So those are the two sort of reasons why we might want to model those sorts of things, especially compounds modulating proteins, because even higher level things such as toxicity is dependent on the action of drugs on proteins. So there's lots of reasons for doing it. But why should we use deep learning to build QSAR models? So when I was looking at deep learning, I was looking at all the image processing and all the image recognition stuff. And it really fascinated me how basically neural networks learn features. They learn feature detectors, that's it. And then it's even more interesting how the features become sort of low level, such as these edges, and all the way up to sort of parts of faces and then whole faces. And it's not just for facial recognition, it's any sort of image. You always end up with these things. It's really interesting. So you've got like the car wheels that form bits of cars, and you see trunks. It's quite hard to see. But yeah, you just learn weird bits of the image. Has anyone seen this image? I'm seeing a couple of nods. So Google trained a big neural network on YouTube, it seemed, and this was one of the higher level nodes that they actually managed to see. It's a cat detector. Like this was all unsupervised, and the neural network managed to sort of recognize a cat, and I suppose that's what you'd expect out of YouTube. But yeah, it's really, really interesting. Good paper. Have a little read of that. So if I take an image, I can extract the different levels of features. So we go from raw pixels to sort of maybe edges or sort of diffuse properties, and then extract facial features, and then finally faces. Increasing complexity and sort of higher level. So I use these. These are my life, depressingly. But what I thought and how I look at molecules is small sort of atoms go and make up what we call functional groups. So atoms make up functional groups, which make up what we might call pharmacophores. And it's basically the same, right? Pharmacophores are sort of complex features, and functional groups are like intermediate features, and atoms are sort of like the raw pixels of the molecules. So I thought deep learning I might not have just jumped on it because it's a sort of massive sort of popularity trending thing. Maybe it might actually be helpful. You can tell this is a paper not by me, depressingly. Lots of other people thought too. Even Google and people are getting into this. Google is not very well known for their sort of pharmaceutical program, but I guess anything deep learning Google's got to do. The other reason was multitask learning. So if you've ever trained on MNIST like this, you probably use a neural network a little bit like this. And you'll see there's 10 output neurons. Each of these are basically a separate task, where it's a softmax there, so they're sort of joined together a bit, but that's sort of basically a normalizing factor. Each neuron detects whether or not a certain number is present in an image. And yes, they shared the weights for all of these hidden layers, and all these different tasks just by themselves might be impossible to learn, but if you pull them all together, you sort of leverage statistical power of huge amounts of data, and you might actually be able to make some progress on a hard problem. So we have things like this, things like this, things like this, things like this. In fact, we've got thousands and thousands of proteins that we might want to model. So maybe that's not such a bad idea after all. So this is what I did. I did some deep learning. Started about sort of start of the year, and yeah, started off trying to gather data, and it sucks. It's really, really, really messy. So one of the big problems is it's always sparse, and compounds are never really tested on all the different outputs. You'll see my data is less than 1% actually filled in, so it's really bad. And it's also really, really noisy, and errors actually up to an order of magnitude coming out of these sort of screens that they do. So really difficult to predict for stuff, and sometimes it's just wrong. There's actually these things called pan-assay interference compounds, which just sort of tinker with how an assay works and giving false readings. So, for example, if your assay is monitoring a drug giving out sort of just doing monitoring a protein doing a process, and you've managed to label it so that it glows if it's working. So yeah, it's sort of fluorescent. What happens if you put a drug in there, but the drug's fluorescent? It just sort of screws up the assay. So yeah, finally, and this is also a terrible, terrible issue. The data is often very unevenly distributed. So the pharmaceutical companies have very limited money, sort of. They've got a lot of it, but this sort of thing is so expensive that when they find something that works, they'll just stick with it. You'll see sort of hundreds and hundreds and hundreds of compounds, all almost exactly the same. They'll have changed one atom, sort of put an atom somewhere else, something like that. And this makes the whole of chemical space really, really, really sort of uneven. Huge pockets and then just an empty chasm. So it's really difficult to actually train models that reflect chemical space rather than sort of the things that some big drug company decided to do. So finally, it's also inconsistent. Data is usually from different assays, from different labs, and it's all measured using different techniques, so they don't really work together. You might think, oh, it's a lost cause. Well, there's this thing called Campbell from the EBI, which is the European Bioinformatics Institute. I like to think of it as the light and the darkness. It collects all the open access data, cleans the data, and links the data to sort of standard identifiers. So, you might have had quite a few screens coming out of Novartis, all targeting the same proteins as screens that have come out of AstraZeneca, but they don't want to play nice together. They won't tell you they're the same target. Campbell goes and finds and just binds them all together, so you actually know what it's like. And you can imagine it's complicated. So they've got this in a nice relational database. Here's the schema. It's quite something for when you start your PhD, your first day. Yeah, just get some data out of this. So I can tell you that's where all the chemical structures are. That's where all the targets are. So all you have to do, SQL madness, and we've got lots of different sort of attempts at doing this, filtering out things that sort of shouldn't be joined together. I'm sure I end up sort of pooling stuff that I don't really want to do, but yeah, it's great. So I've run all of these scripts that I've written to get basically just compounds to targets. I just want a big sort of 250,000 length sort of array of compounds linked to as many activities on as many proteins, which are going to be the target variables. So there's 500,000 activities. So you get about two compounds, two activities per compound, and about 710 proteins, which is tiny, just very, very sparse. So there's a graph. There's another one. This is the dopamine D2 receptor, which is something I did a little project on, so I always tend to use it as an example. You can see this sort of distributed around about here, and this is in log units of concentration. So you see it's kind of normally distributed. A weird little sort of pocket of something that looks very inactive, but yeah, it's too hard to clean all of this up. So anyway, you need to calculate features, and there's clever ways of using deep learning to do this now. But when I started, I didn't do it, and this is basically talking about the project that I did then. So we use these things called circular fingerprints, and this is a compound, it's caffeine again. What we do for every atom, we take the environment at different radiuses. So this is at radius 0, and you see we only have one carbon atom in here. So we take carbon atom, we use a hash function on this list, and it just turns it into a number. Take it to sort of just using modulo 2048, and it gives us 5. So we just set 5 as like the index in our feature array right here. So then you go out to a bigger one, more different atoms in here, hash that again, and it goes to sort of 3 or whatever. And you keep on doing that, and eventually you'll end up with a feature vector. It just means similar compounds will have similar feature vectors because of this. It's a bit more complicated than that because you need to sort of decide different nitrogens in different environments are going to be completely different. So, but it's the same for lots of other things. I won't get into that because this isn't a chemistry conference, is it? So you repeat that for all the atoms, and you'll end up with just a big matrix, really. So finally, getting onto the modeling, yay! This is the fun bit. So I decided to use Keras with Theano. I looked at TensorFlow, but I found back in January that it was in fact TensorSlow. So yeah, I'm really excited to try it now, but it was pretty slow. I did try it out, and it was about 4 times slower. So I start with Theano for now. And then first of all, started out a classification model. I know I said Q in my QSAR, but this is normally how we do this sort of thing. We basically separate what's called hits. These are things with non-negligible activity from misses. which are just things that don't really touch the protein, and it's a way of sort of correcting for the terrible sort of accuracy of the assays. So you normally just binarize around a certain axis, and then that gives you ones and zeros for all of your different activities. And I've already calculated all of those circular fingerprints. So yeah, this is just the network that I used. It's great that you can just sort of put a bit of Python in, and it's actually really readable. So long as you know a little bit about deep learning, it's just pretty obvious. I used, spent quite a long time coming up with this, mind you. Literally sort of hours and hours. The previous speaker was talking about watching the sort of progress tick on by. Spent hours and hours just watching bars go up. But this was the best sort of thing that I managed to find out. Notice use batch normalization. Use batch normalization, it's so good. Makes your models train really quickly. And I found this normal initialization is really good as well. It's all about keeping your accuracy in. Is that a question? Sorry? What is batch normalization? So it's a process for you basically normalize your activations. So that's the output from each node, each layer, so that it's sort of zero mean unit variance. I think it's a bit more complicated than that, but it means you control for the exploding or vanishing gradient problems. Oh yeah, and the final thing: use relus. Don't use those sort of sigmoidy things. Those things tend to work very well. And so yeah, I basically trained it using binary cross entropy because it's a classification model. And yeah, notice I'm not using sort of the softmax here, so you can use binary cross entropy. Yeah. Also, the Adam optimizer. This is binary cross entropy, by the way. It's just some sort of log loss style thing. So I trained it, just using like this. It's like deep learning becomes scikit-learn. It's great. This is what happens basically. You just leave the thing going forever. You could cook an egg on it. So yeah, my computer actually ended up blowing up after I trained it for an excessively long time. It was a 5-year-old computer, but it was a very expensive graphics card. Luckily, I think the graphics card is okay, but I've been trying to get a replacement for that for ages, so I've been actually doing it on my home computer from now on. Just slowed progress a little bit, never mind. So this is the sort of learning curves that you get out. So you can see, yeah, the loss keeps on going down, and basically perfect machine learning problem, right? You can see good fit, and then start overfitting in. The loss keeps on going down, but the val loss is going up. So you want to stop about 60 epochs in for optimal things, and I just plotted some metrics here. And these are all the numbers that come out. They don't look very good, do they? They're pretty low, but realistically, when you're binarizing something that's distributed normally, you've got like the decision boundary is where most of your data is. It's a terrible idea to do normally, but yeah, if you're you have to do something, and yeah, these are pretty good numbers. So I actually compared it to logistic regression, which is what we used to use. You put in the features, and just logistic regression is basically just the same as using a one-layer neural network with no hidden layers at all. You see, it's better. Yeah. I'm not sure how much better. It looks pretty huge, actually. But those are just graphs. Did it really work? So caffeine, my trusty companion, was in the test set. Fortunately, I needed a compound to try things out on. So yeah, the model I'd never seen before, so try to predict for it. You get something that looks like this. So good caffeine. And yeah, basically, The model predicted what I'm feeling. My adenosine receptors have been activated, and I'm awake. So yeah, it's actually, I was really surprised that it worked. It predicted adenosine receptors and monoamine oxidases. So yeah, this is coincidentally this target that we showed before. And then I found this paper. I had no idea that caffeine tended to work on monoamine oxidases, but it does. So yeah, it predicted a thing that I didn't necessarily know about. Yes, so that's all well and good, but I said we needed a why as well as a what. So we want to try and work out some sort of features. This is sort of early stuff, but basically, in an ImageNet, this is my girlfriend's cat, by the way. I just needed to share it with the world. It's so pretty. What you can do is you can slide this black box around and monitor how your output changes. And if the output changes a lot, then you know whatever was under the black box is important. I've definitely seen people do this in image recognition, so I thought, why not try it with a compound? So you basically calculate your features out of here, and maybe your output was 0.8009. That was from the previous one. Now, big black box. This is actually really difficult, and my cheminformatics package, RDKit, which is another fantastic thing if you're ever going to use any cheminformatics package and you insist on open source like I do, use RDKit. It's fantastic. This is all implemented already. It's called similarity maps. There's a paper of it as well. I'm not sure if I linked to it. I probably should have done. But yeah, they just delete it, and then you recalculate it. And you see, if there's a big difference like this, maybe that atom was relevant. So this is what happened with adenosine. Everything was relevant, which I was a bit disappointed. I kind of wanted to see sort of maybe 1/2 of the molecule binding. But if you look at the go all the way back, sorry. All the way back. It sort of rolls around in here, so maybe all the molecule is relevant. It's quite a small molecule, so it definitely could just all bind. I think it's likely that there's a structural analog in the training set, actually, which is kind of cheating. But this was for monoamine oxidase, and I couldn't find any crystal structures of these sort of mounted in a protein to just go and see if sort of the compound sort of goes sort of plugs into the protein like that, but maybe it does. Maybe that's the way it binds. So maybe the black box isn't such a black box after all. So finally, I'm going to regression models. Normally, when you go from sort of a classification one to actually predicting real values, you've got to change everything about your model. I changed one thing, which is to change the activation to linear. Neural networks are great like that. Oh yeah, and change the loss as well. But pretty much it's the same architecture. And using some absolute error here, which is just summing up the difference between what you predict and the actual true value. I looked at squared error as well. This tended to work a little bit better. Now there's only one problem. Can anyone see what the problem is? Obviously not. NANs, because my data was really sparse, and I can't just binarize it and be like, oh, if I didn't know what the value was, I'll just assume it's inactive. I need to know what all of the labels were to just put it into my model here. And you'll notice that I just previously used the string for the loss function. I had to specify a function here, and this is what I had to do. So if anyone needs to train on sort of sparse multitask data, this is how you do it. It's really difficult, at least using Keras. So yeah, you just basically say the costs. You find the cost at a NaN and just say I don't care about sort of the contribution there, and then you get a normal number out when you sum them all up. And you finally are able to train. Honestly, I spent weeks, maybe months, trying to get it to actually train on these sorts of data. And this was the first plot that I got out, and actually didn't manage to improve on it much because I was using the architecture that was good for classification. I think it was good for regression also. Apart from one thing, this had some L1 normalization. I think the model that was producing those other features had those too. As I kind of wanted to have sparser features, you use L1 normalization to do that. So you don't have just a mishmash of every single possible chemical environment contributing in some way to your hidden representations. But yeah, you end up with something like that. And that's how you fit it. These are the plots for all 500, there's 500,000 points somewhere in all of those. You can notice the training set's a lot more fitted, so I definitely overfitted. Yeah, this was before I used the L1 regularization, actually. It gets a little bit less overfitted once you do that. So now to compare to other techniques, you really just end up like outperforming random forest quite a lot. This is just leveraging loads more data sets. I only did it for dopamine D2 receptor because random forest take forever to train, at least on this poor little laptop that had to train neural networks for ages on its tiny little GPU. So I didn't stress it out too much, but it worked out, and I did end up doing it for quite a few other proteins, and it's about like that. So finally, I was just looking at some transfer learning. You do this, but you're basically slicing the last classification layer off, and you're just learning using the hidden representation. So the penultimate layer. That sort of, the idea is those are your like learned pharmacophores, and that should give you a better sort of feature set to differentiate. So I trained it on only 20 proteins. Sorry, yeah, this is what happened. So the Morgan fingerprints are the circular fingerprints that I was using. You see, like it's not that much of an improvement, but it's pretty good. Pretty great. So, anyways, that was just a little going through some deep learning, not on image recognitions. So I'd just like to thank my supervisor and Dr. Günther Kambauer for some good discussion. Günther's the guy who did the deep tox talk, deep tox paper, sorry. My group and the PyData sponsors, and also my funding body, the Engineering and Physical Sciences Research Council, my college, university, and NVIDIA for giving me the GPU that I haven't plugged into any computer for ages because it managed to blow up my old one. Right, questions? Sorry about
Good afternoon. Thank you very much. That was very interesting.
Mm-hmm.
In your network, you have layers that roughly correspond to the circular fingerprint, the functional group, the pharmacophore, and the target.
Yes, basically.
Is that just a coincidence, or is there something that you can do to make one layer particularly target something?
Sorry?
Is that just a coincidence, or is that kind of designed in there?
The final layer is the targets.
Mm-hmm.
That's what we optimize against. So we change the weights specifically to try and get the output layers to be as close as possible to all the known data. So the known data is all the target affinity data. And we hope that the intermediate layers sort of form the same sort of hierarchical feature structure that we see in lots of other different neural network architectures. And
if you went to, say, 16 layers, is that going to help your model, or is that actually going to get in the way?
I suspect I wouldn't be able to train it because you get some errors going all over the shop and probably wouldn't fit in my GPUs and stuff like that. But maybe if you've looked at the ResNets, which just recently won ImageNet, those are really, really, really deep. But the problem with those, you just lost your gradients or they exploded and you couldn't train it. But they use special tricks and can train these really, really, really deep ones. I'd like to try that, but I assume that I would not be able to. I actually haven't tried.
Hi.
Hi.
When you introduced your features, you said that those are ones you started using, but like later some really clever ones came out. Did you actually introduce those later on, or?
No, sorry. I've been using those, but it's I didn't think I'd be able to fit them into the talk, and I haven't published them. And yes, some others have been published. I'd rather sort of maybe next presentation.
Okay.
Come and talk to me afterwards if you want to know about them. I'm happy to talk about them, but I didn't want to put a big presentation out because they're not really finished either.
One technique that I've heard about a lot these last 2 days and not much in the literature about deep learning is trying to see what are the cases that fail and add them to the model. Because you seem to have access to cheap university students to do the experiments and the big machine that empowers them. Yeah. Have you tried that? Is it possible with your very sparse data set?
So adversarial learning? Yeah. No. It would be really interesting. So, but I sadly do not have access to hundreds of robots. It's what one of our collaborators calls his PhD students. I don't have access to a whole team to do experiments. We've got a couple of people who do them, but realistically, that's for pharma to do. This is where most of our data comes. I think about half of it comes from scientific literature. So these are experimental labs, and half of it comes from just big pharma dumping data that they don't think is valuable. I think people, if you had the resources to do it, it'd be really interesting. And sort of, knowing which ones to test, it's sort of almost an active learning style of a thing, which is actually already being explored by a couple of pharmaceutical companies already. There's definitely a big active learning project going on, so sort of, but I haven't got the resources to try anything like that.
Hi. The way that you sort of hashed the chemical structures, is that standard? And are you losing any information by doing that?
It's very standard, and it's state-of-the-art way of representing sort of the structural properties of the compound. So if you get the same compound, they'll have the same features, or the same sort of feature vectors. And similar compounds tend to be similar, and you can do sort of Jacquard similarities and stuff like that to compare them. However, they ignore huge amounts of information, for instance, shape and everything apart from the chemical graph and the atom types.
Right. Yeah. So I was thinking, like, we normally represent them in 2 dimensions, and deep learning, you started with image recognition. I was thinking you might have something in 2 dimensions to represent the structure, and then go with that. But.
Yeah. So I guess you don't really want to represent a compound in 2 dimensions because they're in 3 dimensions. And there's actually been some really interesting work on that actually as well. I'm not sure if they use it on compounds, but they've used it on proteins, where you do a 3D convolutional neural network based on you sort of model binding sites on a protein using a 3D convolutional neural network. The way that those more complex neural network-based feature extractions work is you operate in sort of graph space. So you sort of do a convolution across the graph, so you end up mixing features of nearby atoms, and that's something that I've been looking at and extending. There's already sort of published papers on that, which is really interesting to look at. They're called neural fingerprints, if you want to look.
Okay, please thank Richard Lewis.